So in the next set of videos, we'll be looking at stochastic calculus as we still continue with the stochastic processes playlist. And for starters, we are looking at stochastic integrals. Okay. So first of all, let's have a brief introduction to stochastic calculus. Um, Introduction to Stochastic Calculus. Classical calculus deals with smooth and deterministic functions. Of course, I have a whole course on basic calculus. In case you've not seen that, you want to check that out. It's one of the earliest playlists on this channel. So, classical calculus deals with smooth and deterministic functions, like you see in that particular playlist. However, many real-world systems involve randomness, such as stock prices, physical systems with noise, population dynamics. And to model such systems, we need to use stochastic processes. And of course, a stochastic process, we have seen it amply, that is a collection of random variables indexed by time. And it is a system that is evolving over time with uncertainty, with randomness, and it is given as x of t for t greater than or equal to 0. And we've seen things like random walk, Brownian motion, and all of that. So even Markov chains, right? So now we also try to refresh our memories about Brownian motion, which is otherwise known as Wiener process. So Brownian motion W of t, of sometimes you can say B of t or W sub t, and all these are possible representations. So Brownian motion W of t is the most important stochastic process, right? So that's very important to note. The Brownian motion is the most important stochastic process. And then by definition, a process W of t is Brownian motion if W of 0 is 0. That's the initial condition. At time 0, the motion is 0 also. And then it has independent increments. And then W of t minus W of s is normally distributed with mean 0 and variance t minus s. That's literally the t minus s that are the time in the indices. And then it has uh if it has continuous paths, it follows continuous paths. So the key property of Brownian motion is that it is continuous but nowhere differentiable. So that means that if you try to differentiate normally the W dt like you have for basic calculus, it does not exist. That is why we say it is nowhere differentiable because there's randomness involved. This is why classical calculus cannot be used. So we cannot use classical calculus for stochastic processes. So, and that is why we have an invention for that. So what is the need for stochastic integrals like that? So we want to define integrals of the form integral from 0 to t of x of t dw of t. However, w of t is not differentiable, okay? And then standard Riemann integration will fail in that case. So we define a new type of integral called the Ito integral, all right? So, and for the Ito integral, we have that here right now. So the Ito integral is defined as the limit integral from 0 to t x of t dwt is equal to the limit as n approaches infinity of summation from I equals 0 to n minus 1 x of ti into w of ti plus 1 minus w of ti. So now you see this is, so we now express this integral as a summation as n approaches, as the number of steps approaches infinity, basically. So n is the number of steps because we're talking about a stochastic process, which involves taking steps like that. Then the important feature of the Ito integral is that the function x of t, this function x of t, is evaluated at the left end point. It is evaluated at the left end point, as we're going to see as we move on. So, so of course, you see this is ti. So it's evaluated at ti, right, like that. So the properties of the Ito integral include the following. Number one, the mean of the Ito integral, the expected value of integral 0 to t x of t dwt is 0, settled. And then we have the Ito isometry. The Ito isometry is given like this, that the expected value of the square of integral from 0 to t of x of t dwt is the same thing as the expected value of integral from 0 to t of x squared dt. So in essence, you can see that x of t squared is x of t squared, but then dwt squared is equivalent to dt. That's one thing we can see right from there. And that is exactly the idea of the Ito symmetry. Now, we go on to 48.5 where we talk about fundamental rules of Ito calculus. As we we can see from here already. The key rules here are that dw squared is the same thing as dt. We can see that much from here. And then another part is that dt dw, that is this dt now. So it means that if you have dw squared multiplied by another dw, you are going to get 0 because dw squared is dt. So dt dw is 0. And another thing is that dt squared is equal to 0. So in essence, dt itself should be 0, right? So these rules are essential for stochastic calculus. So we are going to come across this as many times as possible. So dt squared is 0, dw squared is dt times dw is equal to 0. Of course, if dt squared is 0, it means that dt itself is 0. So it means when you multiply anything by dt like that, you get 0. So these are fundamental rules of Ito calculus. And then we talk about the Ito lemma, which you're still going to see in a separate video. But here we are just breezing through it. So suppose the stochastic process satisfies that dx is equal to mu dt plus sigma dw. Then for a function f of x comma t, that we can then have df, that's the derivative of f. Of course, it is going to be a partial derivative, right? It is going to be a sum of partial derivatives at best, right? So because f is a function of both x and t, so it means partial f now is partial f partial t dt. That's when you differentiate with respect to t, plus partial f partial x dx. That's when you differentiate with respect to big X. And then in addition to that, you then have half partial squared f partial x squared. That's the second derivative, dx squared. So it's more like when you differentiate this one again also. So you have half d squared f dx squared dx squared. Since dw squared is then dt, then this becomes that we have df to be df dt plus df dx. So dx itself now is given as mu dt plus sigma dw, like that here, plus 1 over 2 d squared f dx squared sigma squared dt. Now, what we are simply saying is that this is dx, right? So if you square the whole of this now and you put it, if you throw it in here, you're definitely going to have dt squared, right? You're going to have dt squared, and that ends up being 0 there. So you're only going to end up with sigma dw squared. And dw squared is dt, and that's why you have this expression left right here. And that is the idea of Ito's lemma. Okay, so talking about example 1 now, we imagine we want to compute integral from 0 to t of dwt. Of course, we know already that okay, maybe I need to open the worksheet now. You want to compute integral from 0 to t of dwt. Integral. So now we have here we're talking about stochastic integrals, right? Stochastic integrals. And then we are interested in the integral from 0 to t of dwt, dw of t. Of course, we definitely know that if you integrate anything dw, you get w of t. So this is w of t from 0 to t. So that means that you evaluate at t. So you have w of t minus w of 0. Okay, and we already know that for a stochastic process, w of 0 is always 0. So that can go. So we have w of t minus 0. So that means we have w of t, which you can also write as w sub t like this. So that's how that goes. So, and that's exactly why we have integral from 0 to t of dwt to be w of t, or w sub t if you like. So for example 2 then, we want to compute integral from 0 to t wt dwt. So in this case now, if we let f of w to be w squared, right? So using Ito's lemma, we then discover from Ito's lemma that the f, using this expression now, the f dt, blah, blah, blah. So with all of that, you can see there's no t in the expression. So it's easy to just go with f of w to be w squared. So we have df to be df dw. Df dw is 2w, and that'll be times dw, right? Plus the other part now. This part now we have 1 over 2 d squared f, 1 over 2 d squared f dx squared sigma squared dt. So it means that we differentiate this the second time, where is it now? Okay, we are still here. So we have 2w dw, and then we then have dw squared here by the time we do all the process. And of course, the w squared will end up being dt. Okay, so if you throw it into the whole formula, I'm going to take some examples at the end where I'm going to explain all this step by step. So, but I mean, if you follow the formula, you end up getting the w squared. Yeah, and we know the w squared is dt like that. So if you rearrange, what exactly we are doing is we want to integrate, we want to do integral of 0 to t of w of t dwt. That's exactly what we have there. So in this case now, if you rearrange this, now we have that df is 2w. Okay, the w squared is dt, so we've got that yet. So rearranging, we have if you make the w dw the subject, which is exactly what we want to try to integrate here. So if you make it the subject here, it means that we have, so make the w the subject. So it means you take divide through by half. So you have half df, half df, and of course df is dw squared. So half dw squared minus half dt. And if we're trying to integrate, so integrating from 0 to t w dw, which we are looking for, which is w of t dw of t now, then it ends up being the integral of this now, integral from of half w squared t minus half t. So it means if you integrate this whole thing, that's integral of half the w squared dt minus half the wt rather minus half the t the wt. So at the end of the day, when you evaluate all of that, you get half w squared of t minus half t. So, I mean, I know I've missed some steps there, but definitely by the time I solve some examples, you'll understand, you get the gist step by step. Okay, so then of course, we have a Python implementation for this here. So where you get something like this, we're trying to simulate that system we've just seen now. And of course, you see that there's a lot of similarity between the whole random walk, Markov chain, and all that. They tend to be like the same. And of course, they keep changing as we keep running the code, right? So as we keep running the code, we have uh, the shape always shifting like that. Then we can also talk about the Ito integral approximation. So that which we just computed now, we can just do this. This is like half dw squared minus 0.5 t. So it's basically no, half w squared of t minus half t. That's the computation we have done here. That is 0.5 w squared minus 0.5 times t. Okay, and of course t has been defined as 1.0, n is 1000 steps, so dt is t over n, like that. Then we then have the Ito versus Stratonovic integrals. So for the integral w dw, right, which we've just seen there already. So the Ito interpretation that we got tells us that we have half w squared of t minus half t. But for Stratonovic interpretation, the half t doesn't appear. So the difference arises due to how the integral is defined. So for Ito integral, just like what we've seen up there, it is actually half w squared of t minus half t. And for the Stratonovic interpretation, we have half w squared of t. So then what are some applications of the of stochastic integrals? So we have applications in finance where we talk about the Black-Scholes model. We're going to have to talk about this a little bit more in the last video under, I think that'll be the sixth video under stochastic calculus. This is the first one. So that's ds equals mu s dt plus sigma s dw. So in physics, we have the application in diffusion processes and Langevin equations. In biology, we have it in population models with randomness. So we take some practice problems. So I'm just going to flash the questions and then I solve question 10 and 19. So for the practice problems, we have compute. I mean, we've done this already. We already know expected value of w of t is going to be 0. We know that already. Then we have variance of w of t. I think we're going to talk about this in more depth later. But of course, we already talked about some part of it here too. Then we have at the intermediate level, you have those questions now. W of t dwt, that was the one we did before. And then we want to find the expected value of this. So I'm going to be solving question 10, that's integral from 0 to t of w squared of t dwt. So watch out. I'm going to solve it after going through these questions. And then Ito lemmas lemma applications. So you can use Ito's lemma for f of w is w cube. Use Ito's lemma. So it's just like you just take the formula and fix this into it. That's basically what the application is about. That was what we did. We had a problem, then we left it alone and came back to do it later. So I suspect strongly that in solving question 10, we need to use f of w equals w cube. I suspect, but let's see how it goes when by the time I solve it. Then use Ito's lemma for 12. Of course, you can use Ito's lemma for everything. And then at the very advanced level, so that's why I'm solving question 19, integral from 0 to t of e raised by t dwt. So let's go ahead and take questions 10 and 9 like I promised. So coming to question 10, so for question 10 now, question 10, that's problem 10. So for problem 10, we want to compute integral from 0 to t of w squared of t dwt, dw of t. So of course, it makes sense. Just like when we wanted to compute w of t dwt, we had to leave it first and take f of w to be w squared. But in this case, from w squared that I see here, then we need to let f of w be w cube. Okay, so and because applying Ito's lemma, that's how it's going to play out. So from Ito's lemma, right, we can then have that. So using Ito's lemma, using Ito's lemma. Okay, I feel I need to write out the Ito's lemma so we can follow it step by step because I skipped all that in the earlier explanation. So I think this is where I need to really explain that step by step. So I'm going to take Ito's. This is the final result of the Ito's lemma. So let me snip it. Okay, I'm going to snip that and then um, take it to the other page and then follow it step by step. So I take that, then I just copy and then come over here and of course expand this. So using Ito's lemma, which is given like this. Yeah, that's Ito's lemma right there. So what do? We then say that so that df is df dt. So we're using f of w equals w raised to power 3. So from Ito's lemma, then it means that df would be df dt. There's no t here, right? So df dt is functionally 0 multiplied by dt. So that's going to be 0 definitely. Then so we then have df dx. So here we are dealing with w. So df dw. So that's going to be df dw. That will be so dfdw is like 3w squared, all right, and that multiplied by dw. So like this. So we already have it at the level of w. Then plus half d squared f dx squared. That's d squared f dw squared. Df dw. That's partial actually because w depends on w and t. So partial f partial w should be 3w squared, as we already have it. Then partial squared f partial w squared would be 6w, right? That's 6w. So we then have this to be half multiplied by 6w, then multiplied by oh, okay. I think the original form is what we are using here. Let me go back and look and take that. So, this was after everything has been simplified. So, so if we take this, the original one, so that's what we have. Okay. So I can copy this again and take it here. Take it back here. All right. Um, So since we are using this now, so this is so anywhere you see x, since we are talking about f of w, so anywhere you see x, just take it as w. So this will now be dw all squared, right? So from here now we can come down and then we then have df to be 3w squared dw plus half times 6w, that's 3w dw squared. And then you recall that dw squared is the same thing as dt, right? The w squared is the same thing as dt. So it means that this now is going to become df equals 3w squared dw plus 3w dt, because this part now is dt. So, and with that in place, we can then rearrange. So we rearrange. So, because don't forget, this is what we are looking for. We want to integrate w squared of t dw. So that's more like integrating w squared dw. Okay, all right. So we can then isolate w. So this is what we are integrating basically. So if you rearrange, then it means we have df. Okay. Interestingly, df is the same thing as df. We know that f of w is w cubed. So df now, so we can say df is d of w cube. That's d of w cube, exactly. D of w cube, that's df. Okay, so with that in place, then we can then say that we have d of w cube to be equal to this expression here. That's 3w squared dw, which we want to integrate, plus 3w dt. So we can then free this, we can let it go to the other side, or we can transfer this one here, so that we have d of w cube minus, that's d of w cube, right? Minus, minus, minus 3w dt. Okay, what's happening here? Okay, this one has always been plus, right? It's plus, so it's now minus 3wt. So this is now 3w squared dw. So of course, we have now that 3w squared dw is equal to d of w cube, all right, minus w dt, minus, this is, yeah, dw cube minus 3w dt, like that. So of course, we need to divide through by 3, right? Divide through by 3. So then we have w squared dw equals 1 over 3 d of w cube minus, if you divide this by 3, it just remains w dt, because 3 divides, cancels this 3, like this. So at this point now, we have this expression is basically that w squared of t dw of t. So that's exactly this expression. And this is 1 over 3 dw cube of t minus w of t dt. So that's the expression we want to integrate here. So we can then go ahead and integrate. So we can say integrating, that means we have, if we integrate that, we then have integral of squared of t. That's integral from 0 to t, w squared of t dw of t equals 1 over 3. That's 1 over 3. That's integral of 1 over 3 dw cube of t, dw cube of t minus integral from 0 to t w of t dt. Okay, so here we are now. Of course, because, okay, I think I should go step by step, right? This is integral from 0 to t w squared of t dw of t equals 1 over 3 integral dw cube of t, like that, w cube of t, and then that is minus integral from 0 to t w of t dt. So of course, we know integral of d anything remains that thing, right? So this is simply going to be 1 over 3. Integral of d something is w cube of t. So the d integral just cancels the d, kind of, Okay, that's the idea there. And of course, we know this one so well that when we integrate W of t dt, we simply get W of t. All right, we simply get W of t. We simply get W of t from 0 to t. So that then that becomes 1 over 3 omega cube of t, I mean W cube of t minus W of t, right? Plus W of 0. Of course, this is going to 0. So we finally have 1 over 3 W cube of t minus W of t. And that is the final answer like this. So we can then say so integral from 0 to t W squared of t dW of t is equal to 1 over 3 cube W cube of t. Okay, sorry. After integration, this is big T now. After integration, this should already be big T. After integration, this is already big T because it is integral from 0 to big T. Okay, so we have 1 over 3 W cube of t minus integral from, I mean, that's already, okay. This doesn't work. Sorry, this doesn't work because it's not dW of t. So it's better to leave it as integral. So we have integral from 0 to t, W of t dt. So integral from 0 to t, W of t dt. So it's not dW of t. So this better to have it this way. Then we have integral from 0 to t, W of t dt, and then we have integral from 0 to t, W of t dt. So this is how the answer will remain. Uh, Now with the time this one has taken, okay, well, I promised to do that. Let me just do it. So that's problem 19 now. So for problem 19, for problem 19, we need to evaluate. We need to evaluate integral from 0 to t e raised power t dw of t. Okay, so in this case now, it is important to know that this is an Ito this is an Ito integral. This is an Ito integral with deterministic integrand. Deterministic integrand. Okay, so if you then use using the Ito isometry, which is one of the properties of the Ito integral, using isometry, so we have that the expected value of integral from 0 to t e raised power t d w of t all squared would simply just be expected value of we square. Yeah, so that'll be expected value of integral from 0 to t of e raised power 2t. That's e raised power t squared, and then this will be dw of t squared also, and then from here now, that means this is the same thing as expected value of integral from 0 to t of e raised power 2t, e raised power t squared is e raised power 2t, and then this is dw squared of t. So, and then we know that dw squared like that is equal to dt. So that will be expected value of the integral from 0 to t of e raised power 2t dt like this. So, and that's what we have left. So it means that this goes simply to, so we have this, so this means we have integral from 0 to t e raised power 2t dt. Then we can then easily integrate. So we can integrate. So we can then say thus the mean, which is the expected value, the mean is such that the expected value, generally speaking, is okay. I mean, we can compute this, right? So we can still compute this. If we compute this, this is equal to when we integrate e raised power 2t, of course, that will be differentiate 2t, that we get and we get 2. That's e raised power 2t over 2, differentiate 2t, you get 2 from 0 to t. So if you put the big T, of course, you can so half into e raised power 2t from 0 to t. So that means we have half into e raised power 2t minus e raised power 2, 0, like that. So that will be half into e raised power 2t minus e raised power 0. So that means half into e raised power 2t minus 1, like that. So that's computed. And then we move on to, so we can then say thus, the mean is such that the expected value of integral from 0 to t e raised power t dwt, w of t, is equal to 0. That's done. And then on the other hand, we have the variance. So for the variance is what we just got up there as computation. So variance is such that variance is half e raised power 2t minus 1, which you got there. So given. So finally, right? Um, finally, we can then say that finally the integral from 0 to big T of e raised power t dw of t is normally distributed with mean 0 and variance half e raised power 2t minus 1. So, and that's how that ends. So that's it. So with that, we come to the end of this very interesting topic about stochastic integrals. I still have 5 videos under stochastic integrals, so watch out for them. So don't forget to try your hands on the problems. So you have question 1 to 5 here. You have 6 to 9, I mean 6 to 10, like this. Then you have 11 to 15, and finally 16 to 20. I've solved 10 and 19, so you want to go over what I did, and of course try your hands on the rest. So let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. All right. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first or seeing some videos exclusively. You can also request for PDF copies of my notes, or we can hang out together to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.